Welcome to the 24th lecture of combinatorics. So, we were discussing the Fibonacci sequence in the last class as an example of recurrence relations. This is one of the most popular recurrence relations, and this therefore deserves some detailed study. So, we saw a couple of properties of this recurrence relation in the last class, and also derived an explicit formula to evaluate the value, the nth Fibonacci number, right, value of the nth Fibonacci number. Today we will look at a couple of examples where Fibonacci numbers appears as the solution, happens to be the solution, right. So, here is one question: determine the number of ways to perfectly cover a 2 by n board with Dominos. So, what does this mean? So, when we say 2 by n board, we speak of something like this. So, 2 rows and there are n columns, right. So, this is 2 rows and this is 1, 2, 3 up to n. This is the 2 by n board, right. Now, we want to fill this board with Dominos. What do we mean by Dominos? Something like this, say, right. So, this is a domino. That means this can fit here, for instance, like this, right. This is possible, or it can fit it can fit like this, right. So, that means it covers either 2 horizontal squares or 2 vertical squares. So, this kind of blocks we have, which are called dominoes. We have to perfectly cover this 2 by n board. Now, the question is how many ways you can cover it. For instance, I can show one covering here. So, I will right. So, we can cover it like this, or we can next one we can cover like this, and next one we can cover like this, and the last one we can cover like this, right. So, this is a perfect covering of the 2 by n board. There should not be any confusion whether it is always possible to cover or not. It is always possible to cover, because if you had placed for whichever is the n, so we can always cover each. See, every domino can be placed like this, one like this, second like this, third like this, right, fourth like this. So, therefore, it is possible to cover it in this way, right, because it is a 2 by n. So, now the question is how many ways you can cover it perfectly, with how many ways are there to cover. To perfectly cover means no square should be left blank, perfectly cover, left uncovered, cover 2 by n board. So, now the first thing is to come up with a recurrence relation for this thing. What I would say is that let A0, A1, A2 etc. be the sequence of numbers to represent this thing. Let us say A0 is equal to 1, because say it is an n by 0 board. So, let us say we can cover it in one way. If it is A0, so we will say A0 is 1, that is one convenient way of defining it. Of course, one may ask why do we say A0 is 1. So, it is an empty board. For instance, we have 2 by 0 board. 2 by 0 board, we have an empty cover. So, one can say that we cannot cover it, but it, so let us define it as 1, right, because there is an empty cover for that. But what about A1? A1 is a 2 by n board, a 2 by 1 board, right, sorry. 2 by 1 board can be covered in only one way, because it will be just this board, right. So, it can be covered, it can be covered in one way, because there is only one way. You have to place one domino on that, so vertically you have to place. So, therefore, A0 is equal to 1, the number of ways to cover the empty board is 1. A1, number of ways to cover the 2 by 1 board is 1. The number of ways to cover the 2 by 2 board, for instance, this kind of a board, how many ways you can cover? One possible way is to place one domino here, and the other domino automatically has to be placed like this, right. This is one way. Another way is to say, again I am drawing the board. Another way is to place the first domino like this, right, horizontally, right, like this. Now, the second one has to be like this, right. So, there are two ways of doing it. This is 2, A2 is equal to 2. Yeah, we kind of see the Fibonacci sequence here in the first this thing. So, if you had 1 0 before, that would be 0 1 1 2. This is the way Fibonacci sequence is also going. And if you the next one, if you look A3, we should get 3. You can try it out, for instance. So, I see drawing it again and again, it is a little difficult, but so for instance, this is here. There are two ways of doing it. One is you start with this, start this way. Now, we know that this corresponds to a 2 by n domino. We already have seen that it can be covered in two ways, right. Or we could have started with this kind of a domino, right. Then this automatically has to be like this, right. Now, it is just one way to do it. So, that is another one. So, this will be 3, right. So, A3 will be equal to 3. Now, you see in this argument we already got how we are doing it. We are first trying to place the first domino in the horizontal, in the vertical way, then we are trying to place the and then we are counting it, maybe reducing the problem to a previously solved problem. And the other case is when we place the domino horizontally, and then after placing it horizontally, we are after placing it horizontally, we analyze it and reduce it to a previous problem. Now, we can try for the general case. Suppose we know these numbers A0, A1, A2, A3 up to an minus 1, right. Now, I am interested in An. So, this An will be equal to, how will you find it out? So, now this is the 2 by n board, 2 by n board. First, we try placing the domino, the first domino, that here means the domino which covers the first square like this vertically. So, if it covers vertically, then the question reduces to a previous problem, namely the remaining, this red part now, remaining red part is a 2 by n minus 1 domino. How many ways you can perfectly cover it with 2 by n minus 1 board, right. How many ways you can cover it perfectly with Dominos? That will correspond to a n minus 1 clearly. Plus there is another way of doing it, namely if you could have placed the first domino in a different way. Which way? So yeah, you could have placed the first domino this way. Say the first domino you could have placed in this way, right. First domino in the sense that the domino which covers the first square, right. So the point is, if you place the domino to cover the first square in this way, then the two squares just below that has to be like this, right. I mean there is no option here. So say it has to be like this, there is no option here, it has to be like this. Now you know the rest of the things are done. So there is a okay, the remaining things, there is a 2 by n minus 2 board here, because looking from here to here there is a 2 by n minus 2 board, and we have to cover this portion perfectly with Dominos, right. That is a n minus 2, a n minus 2. Therefore we get this recurrence relation, a n equal to a n minus 1 plus a n minus 2, right. So you can see that this recurrence relation will work right from n greater than equal to 2, because so for n equal to 2 case what happens is, in the first case, yeah, n minus 1 is just 1, we know that a n minus 1 is 1, that is true. So if in the 2 case what happens is, this portion, this red portion, this will become empty, right, there won't be, this won't be there. So but we have defined a0 to be 1, so therefore we can say this is the placing, this placing combined with the empty placing for the empty part, right. So therefore it works. Of course if you are not comfortable with that, we could have taken the first 3 values and then we could have started from n greater than equal to 3, right. But even with n greater than equal to 2 it will work. N equal to 1 case, the point is you cannot see the 2 kind of placements at all, the other second placement is not existing. So this argument requires at least 2 squares here, right. So the second type of placement, right. So therefore what we see is here this sequence an, namely the number of ways to perfectly cover a 2 by n board with Dominos, that is an, that satisfies a recurrence relation, namely an equal to a n minus 1 plus a n minus 2 for n greater than equal to 2, and which is same as the recurrence relation satisfied by the Fibonacci sequence. So can we assume that then can we immediately infer that a n equal to f n and write a n equal to yeah, the formula for f n, right, maybe 1 by square root of 5, right, into 1 plus square root of 5 by 2 raised to n minus 1 by square root of 5 into 1 minus square root of 5 by 2 whole power n. Can we write like this? No, because it's, as we have seen, it's not perfectly matching, this is not correct, right, this is not correct. Why? Because I will write down the sequence once again, this is a0, a1, a2, a3 like this, this is 1, 1, and then we have here we have, how much was a2? A2 was 2, right, A2 was 2, A2 was 2, 1, 1, 2, 3, like that only it was going, 1, 2, 3 and so on. But Fibonacci sequence was different, f0, f1, f2, f3, if you take, this was 0, this was 1, this was 1, this was 2 and so on, and then it is correct 3. So, in other words, this is obtained. So, we have to map this to this, this to this, this to this and so on. So, in other words, a n is f n minus a n is f n plus 1. So, a 0 will be a f 0 plus 1, that is f 1, a 1 will be f 2, a 2 will be f 3 and so on. So, we get a n equal to f n plus 1. So, now we can substitute the formula a n equal to 1 by square root of 5 into 1 plus square root of 5 by 2 raised to n plus 1 minus 1 by square root of 5 1 minus square root of 5 by 2 whole power n plus 1, and this is true, right. Yeah, this is because Fibonacci number sequence was true for all n greater than or equal to 0, this will work. So, that is, this was one instance where the Fibonacci numbers appeared. So, of course, when we talk about perfectly covering the 2 by n board with Dominos, one may not really guess that there is Fibonacci numbers hiding inside, right. Similarly, we will look at another question now. So, here determine the number of ways to perfectly cover a 1 by n board with monominos and dominos. Okay, this is the same question put in a slightly different way. So, now we are saying that our board is only 1 by n. So, this kind of a board. N is 1 by n. Now, we are allowed to use not only this kind of things, these are dominos, but also pieces like this, right. Now, we want to perfectly cover it. It is clear that we can perfectly cover it. For instance, we could have taken first a domino, then another domino, and then another domino, until, for instance, if n was an even number, we would have perfectly covered it that way, but the last one we can cover with a monomino if it is an odd number, right. So, therefore, it is definitely possible to cover. Now, what we are interested in is in how many ways you can cover it, and I told you that the question is similar to the last one, because because we can see that. So, if you imagine, we suppose we extend it to a 2 by n board like this, right, 2 by n board. We just add an imaginary second row also, and then ask. So, the previous question here, that means we want to perfectly cover it with monominos, then that will correspond to the current question. Why? Because if you get a covering of this 2 by n board with dominos, then we have a corresponding covering of the 1 by n board, including consisting of only the first row here, right. Why? Because we just take the induced one, because for instance, if it was a first domino like this, then this is also a domino for the the another one, for instance, second domino was, suppose it was like this, then we will consider here a monomino, cutting it off the later part. Similarly, if there is a monomino here, domino like this, a vertical domino will give a monomino in the upper part, right, and a horizontal domino taken will give a domino itself on the upper part, right. So, therefore, naturally there is a corresponding covering of the first row with dominos and monominos for every perfect covering of the 2 by n board using dominos. Just the correspondence is that wherever we see a horizontal domino used, then in the first row we use it as that means it is a domino, If it was a vertical domino, we just cut out the lower part and then take a monomino in the upper part, right. Similarly, the converse is that, I mean, we are setting up a bijection between the two problems, as we always do. So the suppose we get a covering of the first row using dominos and monominos. So we can definitely extend it to the 2 by n board by whenever we see a monomino, we just extend it downward by making it this thing. Whenever we see a domino here, suppose we see a domino here, right, then we put a corresponding domino in the 2 squares just below it, right, like this. If it's a monomino, we will extend it like this. If it's a domino, we will just put a domino below, right. So therefore we can correspondingly extend it to a covering of the 2 by n board using dominos alone, right. So any covering of monominos of the 1 by n board using only monominos and dominos can be extended to a covering of the 2 by n board using only dominos. And the correspondence is clear. For instance, it is a bijection. There is no need to explain it further. You can see from the picture that right, its coverings correspond to, there is a 1-to-1 correspondence between this thing. Therefore the answer is same. That means if you count now Bn, let Bn denote the number of ways to cover the first row, that means 1 by n board with monominos and dominos perfectly, that is same as an, right, an equal to Bn, right. So on the other hand, if you wanted to proceed like independently, you could have argued like the same way. For instance, in the, you just after getting the getting a few first values, like for instance A0 is equal to 1, A1 is equal to 1, A2 is equal to 2. Why A2 is equal to 2? Because you can either have a domino like this, or you can have 2 monominos like this. You can have one monomino and another monomino like this, 2 monominos like this, right. So that's therefore it's 2, right. Or and then you can argue to get the recurrence relation. What you can argue is, so what is Bn? Bn means the number of ways to perfectly cover the 1 by n board, right. So we just concentrate on the first square here. So if you are using a monomino, then you know the remaining n minus 1 by n minus 1 board has to be covered using monominos and dominos. That can be done in Bn minus 1 ways, right. On the other hand, if you had decided to cover the first square and second square together using one domino, then what happens is it's equivalent to Bn minus 2, because the remaining portion, that is an 1 by n minus 2 board, it can be covered, perfectly covered using monominos and dominos in Bn minus 2 ways, right. So this will be the recurrence relation. This is this argument works for n greater than or equal to 2, right. So therefore it's the same kind of problem, but we can see that the Fibonacci recurrence relation is coming here also, right. The next one is a slightly different problem that also has this Fibonacci numbers hidden in this. So let S0 is equal to the empty set, and for n greater than 0, let us just define Sn is equal to 1, 2, 3 up to n, the first n positive integers. Now let An denote the number of subsets that contain subsets of Sn, right, that contain no consecutive integers. Find and solve a recurrence relation for An. Or means what is this number? That's what we are asking. Now here, for instance, A0 is what? Empty set. How many subsets of empty set is such that there are no consecutive integers in it? We can take it as 1, because that empty set is like that, there is nothing in it. So how can any consecutive integers be present in it? Now for S1 equal, this was S0, S1 is this one, just one. So you can take, there are two subsets to S1, namely empty set and that itself. Both are okay because they do not have consecutive integers, because maximum one integer is there in it, therefore they cannot have two consecutive integers. So A1 is equal to 2. But when you say S2 we have to be more careful because this is S2. So there are 4 subsets of it. Empty set, that is fine because it does not have any consecutive integers in it. Of course any of the singleton subsets are fine because singleton subsets cannot have consecutive 2 integers, and then but then you cannot take the whole full set because 1 2 has consecutive integers in it, 1 and 2, right. So therefore it is not 4, it is 3. So A3 equal to 3, and now if you look for 4, right, so you will see that I mean this was A2 equal to 3. So now this is now look at A3, is 3 equal to A3, 1 2 3. Now you want to count how many are there, right. So definitely empty set is fine, all singleton sets are fine. Now if you take 2 element sets, out of the 3 things 1 2 is not allowed because it is consecutive, 2 3 is not allowed, but 1 3 is allowed, we get 1 there, right. Now the full set is not allowed, 1 2 3 has consecutive integers in it. So this much is the answer. So that is 4 plus 1 5, 5 is the answer, 5 is the answer, 5 is the answer. Now we see the Fibonacci numbers here, just that Fibonacci numbers F0 is equal to 0, F1 equal to 1, F2 equal to 1, F3 equal to 2, F4 equal to 3 and so on. So just that you can see that here the mapping, if at all this is the Fibonacci numbers, the mapping has to be here A0 equal to F2, A1 equal to F3 and A2 equal to A3 and so on. The question is will it be different later? As of now it seems to be okay because up to here at least 3 numbers we have verified. So later will it be different from the corresponding Fibonacci numbers? We are seeing we would like to conjecture that an is equal to Fn plus 2, right, as we can see from here. A0 is F2, A1 is F3, A2 is F4 and so on. So I would like to conjecture An is Fn plus 2. Is this correct? So we want to prove that this is correct, right. Now how will we prove it? To prove this we consider a Sn. Now Sn is like this, say 1 2 3 up to n, right. Now let us say up to n minus 1 we have figured out the numbers, that means n minus 1 we know the sequence A0 A1 up to an minus 1 is known, right. Now we want to get a relation, I mean to an we want to express in terms of these previous numbers, right. How will you know? So this Sn being 1 to n, so we can consider 2 cases. We are counting the subsets A, so that means we are counting A subset of Sn such that A does not have consecutive integers in it. Now these sets, suppose this is a family F, these sets we have two types of A's, A's that contain n, A's that do not contain n. So let us say we will put it as F dash and F double dash. So F dash, this is also a subset of F, this is also a subset of F. So we will put it as F dash is equal to the A's from F such that n element of A, and F double dash is such that A's from F with n not element of A. We can definitely partition F into F dash and F double dash. This is exhaustive, right. So, and mutually they are disjoint also. There is if an A is in F dash, then that A cannot be in F dash and vice versa, right. And every A will be one of this type, right. It may have n or may not have n, that is all. Now let us try to estimate F dash and F double dash. So the cardinality of F dash and F double dash, and then sum it up, we will get the cardinality of F, right. Now this F dash, that means when n is there in A, then what can happen is, so what is clear is, because n is there, n minus 1 cannot be there, because otherwise n minus 1 and n together is consecutive integers, then that cannot be present in a valid A, right. So that is our condition. So we have up to, so the remaining part of A are coming from 1 2 3 up to n minus 2. So now these sets also should also be such that they should not have consecutive A's. So then what we define is, from F dash, for we define F say for each A element of F dash, we can consider A dash such that A, that is A bar n, right. We just remove n from it, because each A in F dash has n in it, we just remove it and we get a dash in it. It is the cardinality of such those sets are same, because it is not possible to get the same A's by removing. So you take two different sets in F dash and remove n from it, you will not end up with the same A dash. Why? Because each of these members in F dash had n. Now if you remove n from each of them and end up with the same set, that means original two sets were also same, right. That means the cardinality of F dash can be found by finding the number of A dashes, right, and those A dashes contain only members from 1 2 3 up to n minus 1, because n we have removed, n minus 1 cannot be there, because originally we had the property that consecutive integers were not present. N is present, n minus 1 cannot be present. So now it is coming from 1 to n minus 2, and no consecutive integers are there in any of them, and naturally this number is A n minus 2, because this is the number of sets you can form from 1 2 3 up to n minus 2 without having any consecutive integers, any pair of consecutive integers in it, right. On the other hand, to estimate F double dash, what we can do is, we notice that n is not there. So if n is not there, it is coming from 1 2 up to n minus 1, right. Now we could as well say we are selecting sets from 1 2 up to n minus 1, 1 2 3 up to n minus 1, such that no consecutive integers are present. That number is clearly, this number F double dash cardinality is clearly A n minus 1, right. So therefore the cardinality of F is cardinality of F dash plus cardinality of F double dash. This is A n, this is A n minus 2 plus A n minus 1, as we have seen. So this satisfies the Fibonacci recurrence relation. So, no wonder that we are seeing the pattern. And this you can see that this argument is true for n greater than equal to 2, because in the first argument when you found out f dash we removed n and then plus 1 automatically went away, and now we have the empty set, right. So, in the other thing we just removed n. So, we have, because n is 2, then we will have one number, then we can take n minus 1. So, that is fine. So, therefore, it is this recurrence relation valid for n greater than equal to 2, and as we have seen the correspondence, the first initial values when you check, we see that the recurrence relation is valid, but just the initial values are a little shifted in the sense that A0 correspond to F2. So, therefore, we can infer that An equal to Fn plus 2 as we conjectured, right. And this is, we know the value of this thing, this is 1 by root 5 into 1 plus root 5 by 2 whole power n minus 1 minus 1 by root 5 1 minus root 5 by 2 whole power. So, this is n plus 2, sorry, n plus 2. So, that is, so here also we can see, again I repeat that the problem was that we have taken the integers 1 to n, and then we asked to find the number of subsets of this set 1, 2, 3 up to n, such that no consecutive integer is present in it. So, looking at this problem, one may not think that it has something to do with the Fibonacci numbers, but the answer happens to be the Fibonacci numbers, just that it is a little shifted. So, nth Fibonacci for n natural numbers we are getting the n plus 2nd n plus 2th Fibonacci number, that is all. So, like that the Fibonacci numbers have several interesting properties. So, here is one property which is a little slightly different thing, but it is interesting. I can state it, but probably I will not prove it. Let us see. So, it is not because it is difficult to prove, but to save time. So, it says Fn equal to n minus 1 choose 0 plus n minus 2 choose 1 plus up to n minus k choose n minus k minus 1, where k is equal to n plus 1 2. So, let us say, so this is which says, you remember the Pascal's triangle. So, Pascal's triangle was written like 1. So, for instance, here 0th row of the Pascal's triangle, the 0th row of the Pascal's triangle contained just 1, n choose 0 choose 0, right. This is the 0th column, say this is the first column, second column, third column, like that. So, now first row of the Pascal's triangle contained 1 choose 0 and 1 choose 1, 1 and 1, right, 1 and 1. And then second row the Pascal's triangle contained 2 choose 0 1 and 2 choose 1 2 and 2 choose 2 1, and 3 it is 1 3 3 and 1, right. And fourth it was 1 4 6 4 and 1, 5 it is 1 5 10 10 5 1, like this. So, now it will keep on going like this, right. Now, that formula says, for instance, the Fibonacci number, 5th Fibonacci number. So, let us say 5th Fibonacci number, right. It says it is equal to, you start from the previous row. So, that 5th Fibonacci number, so 5 here, then you go to the previous row, and then here you start from n minus 1 choose 0 and then go backward in the row. I mean go backward in row wise, but then keep increasing the column numbers. That means along a diagonal you go upward. That is what it says, right. Along a diagonal you go upward. So, the previous, so the first number, so we can this is the first number, which so n minus 1 choose 0, which is 4 choose 0, that is to begin with, plus n minus 2 choose 1, right, which will be 3 choose 1, right. That means here 3 choose 1, and then here we will take n minus 2 choose 2, that will corresponds to 2 choose 2, right. Here the column numbers are increasing 0 1 2 like that, and the row numbers are decreasing 0 1 2 like that. So, here it is like this. So, it is along a diagonal. So, next one what happens is this here 2 minus 1 is 1 and 2 plus 1 is 1 here. So, 1 choose 3 will come, from now on it will be 0 up to here only. So, what is this? This is 3 plus 1 plus 1, that is 5. If you sum up these things, right, you will get 5, and the fifth Fibonacci number is indeed 5, because the first Fibonacci number 0 1 1 2 3 and 5, right. So, this is the fifth, 0th, 1st, 2nd, 3rd, 4th, 5th. Fifth Fibonacci number is these are adding up to 5. It's indeed an interesting property, right. And so, the next Fibonacci number has to be 8, right. So, let me see. So, for instance, when I go for the 6th one here, so it will start from here, then it will come here, and take this thing. So, when you add up all these things, 1 plus 4 plus 3, that means 6, 5 plus 3 8. So, it is working out. So, what we claim is that just go to the previous row. For instance, when you want to find the nth Fibonacci number as a sum of entries in the Pascal's triangle. So, it's the nth row we are in. So, we go to the n minus 1th row, start with the 0th column, and then go backward, go upward, right. That means the rows are decremented one by one, and columns are incremented. This is some diagonal way you go upward, right. So, and add up till when you will hit, so after some time there will be all zeros, then you just add up to here, you will get 8. So, get the corresponding number, and this proof does not use anything complicated. You just have to do some manipulations. So, what I do is I leave it to the student to figure out, because if I spend time on that, I will like I spend a lot of time on that. So, I would rather leave it to the student. Now, I will go further to formally consider some more general kind of recurrence relation. So, we just studied Fibonacci recurrence relations here. So, now we will consider the same type of recurrence relation, but in a generalized setting. So, we will consider this thing called linear homogeneous recurrence relations. This is the next thing, right, linear homogeneous recurrence relation. So, what is this linear homogeneous recurrence relation? So, we have some sequence H0, H1, H2, H3, H4, H5 like this, Hn, right, like this. Now, suppose you can find a formula for Hn in terms of the previous things, that we have a formula such that Hn equal to something times, let us say A1 times Hn minus 1 plus something times, let us say A2 times Hn minus n minus 2 plus up to A k minus 1, sorry, A k h n minus k. In other words, we are combining the previous k terms. So, when you want to get this Hn, we are combining the previous k terms 1, 2, 3 up to k terms here, and in some way. So, that is coefficients are like capturing that. So, whatever I am talking about, some way what is. So, that is in a I can say in a linear way, right, and because linear way, because we do not write like hi into hj here, right. We do not multiply two different previous terms together, they are separate, but just that they get some other multiplier, maybe a constant, maybe a function of n. This a1 can be a function of n in general, but never it will never involve another previous term. It is not that a1 contains some hi which was before, right. So, in that sense it is linear, and finally, okay, we also add some term which does not even contain, it is not even multiply this thing. Here we say that this is a linear recurrence relation, and also we say that its order is k. It is a linear recurrence relation of order k, and then as I mentioned, these coefficients we are using a1 to ak are can be functions of n, they can be constants also. If they are constants, then we say that this is a linear recurrence relation with constant coefficients, order k and constant coefficients. So, it is not necessary that always the constants are coefficient, but it can be constants also in the simple cases. Now, for instance, I can give some simple examples. For instance, our Fibonacci recurrence relation, it was like fn equal to fn minus 1 plus fn minus 2. You can clearly see that here k equal to 2. This is a second order linear recurrence relation. I mean, because we have two previous terms we are combining to make the nth term, right. And here our a1 is equal to 1, similarly a2 is equal to 1, and there is no bn is 0, right. Similarly, we can consider see, not that when bn is 0, we can also have one another qualifier, it is called homogeneous recurrence relation, homogeneous linear recurrence relation. When bn is equal to 0, it is called homogeneous recurrence relation, and the other terms are linear homogeneous recurrence relation, right. Now, for instance, you can consider this recurrence relation which appears in the geometric progression, namely say an equal to q times an minus 1. Here is a first order one, because there is only one previous term we are using to get the next term, and a1, sorry, yeah, so I am sure, so we should have, so let us say we will use hn equal to q times hn minus 1. So, it is first order is 1, this a1, the first coefficient is 1 on q only, and then Bn equal to 0 here, that is a homogeneous one also. Or this is of course, I mean if q is a constant with we can also say that it is with constant coefficients, right. In the Fibonacci recurrence relation we had constant coefficients. Another one maybe we can consider this recurrence relation n into hn minus 1, right. What does this give? This is hn, you can easily see is n factorial. Why? Because if you put h1 equal to 1 or h0 equal to 1, h1 equal to 1. So h0 equal to 1, then h1 will be 1 into 1, h2 will be equal to 2 into 1, that is 2, h3 will be equal to 3 into 2 into 1. So h4 will be equal to 4 into h3, that is 4 factorial, and so on, right. This is the recurrence relation for n factorial. So here this is also a linear recurrence relation, just that, so of course here the first order one, because there is only one previous term we are using, and this a1 is n here, this is not a constant, right, this is a function of n, and we do not have any bn equal to 0, it is a homogeneous one of course. So there are several such examples we can consider, just to make sure that the student understands the keywords. Now we quickly move on to the important thing. Yeah, one thing is of course, so we can write this relation, so whatever I have written here, this relation for only for n greater than equal to k. Why is it so? Because we need k previous terms to define this thing, otherwise there is no point saying that hk, what is hk minus 1 is equal to a1 into hk minus 2 plus like that. In the end what happens is a k into h k minus k will come, sorry, k minus 1 minus k will come, that is a k into h minus 1 will come, which is not defined. We have the sequence starts from h0, h1 up to hk minus 1, we have k terms, right. But if you are only taking up to hk minus 2, we have only k minus 1 terms, but we have defined this thing for k terms. Of course, one more thing we have to be careful about, when I say order is k, it is important to note that we are indeed using ak as we are claiming that ak is non-zero, because hn minus k we are going all the way down to the n minus kth term, means k terms down we are going, but in between terms we may not use, but we are indeed using the lowest term which is told here, that is ak is assumed to be non-zero here in this definition, ak is assumed to be, otherwise we cannot say it is a kth order, because see if this was 0, then what will you do, we would just stop in the previous term and ak minus 1 hn minus k, we can as well say that its order is k minus 1, right, order is k minus 1, that is also important. So the order means, so it's important to note that we are not really worried about all the AIs being non-zero, the first AI is 0, it is okay for us. So what we are worried about, we just go down from the highest term downward, right. The least term we are taking, should have a non-zero coefficient. The least term we are taking should have a non-zero coefficient, right. That is why, that is where the kth order is coming, because k previous terms are used is coming from there, right. Otherwise we would have thought that we are going only k minus 1 terms downward. And yeah, so the what is the thing? Yeah, we have defined the kth order homogeneous recurrence relation. Yeah, a k is not equal to 0 and the quantity v n. Yeah, these are the points. And then now the next thing is a method to solve a general, I mean to get a general solution for this kind of homogeneous recurrence relation. That is what our aim is, right. Of course, we have seen that many interesting recurrence relations fall into this category. So, it is worthwhile to attempt to get a strategy to get a general solution for this recurrence relation, right. We will do it in the next class. Thank you.